The purpose of this tutorial is to go through the preliminary steps to set up your problem before you move to HECRAS. So anytime you're doing a numerical model, oftentimes there's a lot of work that you can do ahead of time that will set you up for a successful solution. And we're going to go through those basic steps with our example problem that's given here. This is example problem 5.2 in the textbook, page 195. And the basic steps, just to summarize what we're going to do here, the first thing we're going to do is define the geometry for the channel. And we'll spend a little bit of time on this because I'll give you some specific terminology that HECRAS is going to use. And then the next thing, after we define the channel geometry, we'll actually use Microsoft Excel to make things a little bit easier for us when we get to HECRAS. Then we're going to develop a qualitative water surface profile, similar to what we've done in class, so that we have an idea of what our numerical solution should look like. Okay, and that will help us evaluate whether our result is successful or not. And we'll follow basically the same procedures that we go through in class with that to develop the qualitative solution. And then in the next tutorial, we'll start with the quantitative solution, where we'll actually take the information we developed today, put it into HECRAS, and get a numerical solution. Okay, so I'll quickly read through the problem. We'll use SI units here. I think looks like it gives both, but we'll go ahead and work in SI. And so what we have here is a trapezoidal channel, has a bottom width of B of 8 meters and a side slope ratio of 2:1. The Manning's N of the channel is 0.025 and is laid at a slope of 0.001. If the channel ends in a free overfall, compute the water surface profile for a discharge of 30 cubic meters per second. Okay, so we're given basic information about the channel geometry and the flow rate. Okay, so if you're thinking about the geometry, we have basically 3 components we need to consider. One is elevations along the channel. The second is horizontal distances along the channel. And the third is the cross-section geometry. I'm going to start with the elevations. This is very important. HECRAS deals in relative elevation, so you have to decide where an elevation of 0 is. And unless you have another reason to select otherwise, I like to make the downstream end an elevation of 0. So we'll set this as 0 meters. Okay, if you knew the elevation in terms of mean sea level, you could select that. That's a reason why you might not use 0. But for the types of problems we'll do in class, I just recommend setting the downstream elevation as 0. And that means as we move up the channel, upstream direction, that we will have positive elevations. And so at the end of the channel here, we have another elevation. But we don't know actually what this elevation is because if you notice in the problem, the length of the channel is not defined. So we would actually need this to go into HECRAS. So what I'm going to go ahead and do is just define the length of the channel. And I've picked a value that will work well for this problem, 1,400 meters. So the length of our channel horizontally is 1,400 meters. Okay, and if you take 1,400 meters, combine it with our bed slope. So here's a 1, here's 0.001. We know that this change here in elevation as we go from the downstream end here to the upstream end, if we were to call this delta Z, this would be 1.4, right? Because of our bed slope of 0.001 and the length of our channel. And so this elevation here at the end is going to be 1.4 meters. Okay, so there's your vertical elevations, or vertical distances on our channel. The horizontal distances, HECRAS defines something called a river station, and that just marks the horizontal distance along the channel. So similar to elevation, we have to decide where's river station 0. And my rule of thumb is, again, the downstream end, to go ahead and set this as river station 0. I'll put a little cross through the 0 so it's not river station O, river station 0. And then when we get started, the only other river station that we need to define is at the end of the channel. So what is the river station here at the end of our channel? And this may seem a little bit counterintuitive at first, but HECRAS counts river stations positive in the upstream direction. So this is actually going to be river station 1400. You might think it would be river station negative 1400, but it actually, again, it numbers positive upstream. And we can talk in class about why that is. Okay, and once we're at this point, we've basically set up our elevations and our horizontal distances along the channel. So we're ready now to move on to the cross sections. Okay, so if we look at the cross section geometry, we are given a bottom width of 8 meters and then side slopes of 2 to 1. This will obviously won't be to scale, but I'll do the best I can. So again, we have B of 8 meters and side slopes of 2 to 1. Okay. Now, and as you can imagine, in an actual trapezoidal channel, we would also have, ground surface out here, right? Like so. And so our channel is going to have some depth, say h, of some value. This is not given in the problem, so I found another value that will work. And for this case, we'll just use 2 meters because you're going to need this in HECRAS to really define the geometry of the channel. Because HECRAS wants to know when water might leave this area, which we would call the main channel, and at a high enough discharge, flow is going to leave the main channel and enter into this region, which HECRAS calls the floodplain. Okay, so you have floodplains on both sides, and HECRAS calls these the left bank floodplain and the right bank floodplain. Okay, and there's kind of an imaginary dividing line between these, like this. So this is your main channel region. Anything then to the left and right of the main channel, this is floodplains. And the reason HECRAS separates them is it allows you to actually specify a different roughness, like Manning's N, for your main channel and floodplains, which if you think about it might make sense. The main channel might be sand or gravel. The floodplain, though, may have trees and vegetation and things of that nature. And so the way that HECRAS does this is it allows you to specify basically what they call bank stations, which define where the main channel ends and the floodplain begins. And when we put these into HECRAS, we're going to see these red dots like that. And so these are called in HECRAS bank stations. And they just define where the main channel is. Okay, so bank stations. Okay, and once we're at this point, we have pretty much defined now the cross-sectional geometry as well. So again, we now know vertical elevations, we know horizontal distances, which HECRAS calls river stations, and we know the cross-section geometry, the main channel, and where the floodplain begins. So what I recommend next is that we go into Microsoft Excel and just set up some of these numbers. The reason is we can copy and paste very nicely from Excel into HECRAS. So let's go to, I've set up an Excel file here. Let's have a look at it. So again, here's our problem 5.2 in page 195 of the text. I've put all of our givens here. At this stage, the only important givens are really the geometry ones, are B, bottom width, M, side slope, and bed slope. And then I added these additional characteristics. The length of the channel is 1,400 meters, and that gives us a delta Z, a change in elevation of 1.4 meters. Note, this is not the delta Z like a step up and step down in the channel like we did with specific energy. This is actually the change in elevation over the entire reach, the 1,400 meter reach. Okay, the next thing we need to do is define the cross-section geometry in terms of numbers so that we can basically copy and paste. And I started at river station 0. So again, this is that lowest elevation cross section, the downstream end of our reach. And if you do this, Heckras breaks up cross sections into stations, which are horizontal distances. These are perpendicular to the flow direction. And then elevations, which obviously are vertical. And if we start at station 0, it actually doesn't matter as much where you start here. This is all distances are relative again. We start at station 0 and an elevation of 2. This is this point here, the top of our bank. And then our trapezoid is defined by 4 points. So then if we have a slope of 2 to 1 and an elevation of 2, our next point is at 4, 0. And then we add our bottom width of 8, and so we get 12, 0. And then we add our side slope of 2 to 1 over a vertical distance of 2, and we end up here at 16 and an elevation of 2. So these 4 points, and I've plotted them here so you can see very clearly we do have a trapezoidal channel. Notice that the scales are different, so it doesn't actually look like a 2 to 1 slope, but it is in fact 1. And then note that I just noted here at the bottom, channel depth is not given for this problem, but we're going to go ahead and use 2 meters. That will work. Okay, and once you do this, we're all set. You may say, well, what about the upstream end or other potential cross sections that we might want to look at? Once we get the first one set up for a prismatic channel like this, Heckras has some tools which will allow us to put the geometry together very quickly. But in general, I always set up at least the first one in Excel because it allows me to visualize it with a plot and then copy and paste once I know that it's correct. Okay, and so that wraps up the geometry component. We basically, again, we defined elevations, we defined river stations or horizontal distances, and the cross-section geometry, and then we set up one of our cross sections. And again, I recommend the downstream boundary. We set up the downstream boundary cross-section in Excel. And one thing I want to note here is note that our lowest elevation is 0. This corresponds with where we set 0 at the downstream end of the channel. So make sure that this aligns well with your drawing. Okay, so the next step is now, excuse me while I click through here, we need to develop a qualitative solution for our problem. Okay, and as we've done in class, the first step is to classify our slope. So we're given all the numbers here, the geometry, and roughness and discharge to classify the slope. The easiest way to do this is to use tools that you've already developed in MATLAB. And so let's go ahead and bring MATLAB up. And you'll notice that I've put a nice script together. You can do something very similar to this that you see right here that will allow you to do these calculations very quickly. So I'm going to talk through it, but honestly, this is a step that once you have this up and running, it should be, less than a minute, honestly. The hardest part is to make sure you get all your givens in correctly. So your flow rate, your channel geometry, in this case is trapezoidal, so bottom width, side slope, ratio, and your bed slope, and then your Manning's and then again, I use this U flag. I set it to SI units. You may have inputs for that are different from this if you wanted to actually input gravity and the Kn in Manning's equation based on whether it's SI or English units. But again, I just do it here. Then you'll notice I'm going to calculate the critical depth, calculate the normal depth. That's all we need to classify our slope. I'm going to write the output to the command window so I can make a decision. So notice as I click through this, it's going to be rather quick. Click through the givens, calculate the critical depth, calculate the normal depth, and then I'm going to go ahead and F9 these so we can see what the answers are. And you can see here, YC is 1.03 meters, normal depth 1.75, and a Froude number of 0.4. So with this information, we can now classify the slope. And there's basically 2 ways you can do this. One, you can note, and I've written these here at the bottom of my script, you can note that your normal depth is higher than your critical depth, therefore it's mild. Or if you like, this is equivalent. Flow at normal depth is subcritical, right? We have a Froude number of 0.4. Therefore, we also have a mild slope. So either way you want to look at it, you get you're going to get the same answer. Okay, so once we've done this, again, the actual numbers here don't matter at this stage. It just matters that the slope is mild. So I'm not going to try to draw, I'm going to sketch on our figure now, but I'm not going to try to draw this to scale. Okay, I just know that it's a mild slope. Again, mild slope, I'm going to go ahead and put in my normal depth line, same as we would do for any qualitative water surface profile. And I apologize with this pen, the drawing is going to be a little bit messy. I'll do the best I can. A normal depth line is obviously parallel to the bed slope, and I did not too bad of a job there. And then let's go ahead and add our critical depth line. And again, the thing that matters here is that critical depth line is in between the channel bottom and the normal depth. I'm not going to try to actually draw them to scale, even though we do know the values for each. I'm just not, that's beyond my ability as an artist. Okay, and so we have our normal depth line, our critical depth line. Okay, so what's the next thing that we need to look for? We need to look for that boundary condition. Again, we're solving a differential equation, so we need a boundary condition. And remember, in hydraulics, we call this a control. And if you read, probably when I first read the problem, something jumped out at you. It's a classical control that we've talked about in class, and that's this channel ends in a free overfall. And so our water surface at the end of the channel is, say, down here. So we have something like a reservoir, or maybe it's flowing into, reservoir pond, something like that. Okay, and you know from class when you see this, we have a known water surface elevation. Again, that's our control. We have something that controls the water surface elevation for a discharge. We know it passes through critical depth, YC, just about at the end of the channel. And so if we go back to our water surface profile, we'll see something at the end like so, flowing into the reservoir. And we use this. This is a classical case. We can now see, oh, I forgot to add one thing. We should always note at the beginning, so you don't forget. I should have written this, right? But that's okay. We talked about it, but writing it always helps. Now you can see if it passes through critical depth, basically this is going to be your M2 profile. As we saw an example similar to this in class, right? And so, again, we don't know the exact curvature, but it's going to do something like this. Whether it reaches normal depth or not, we don't know. HEC-RAS will help us with this, but qualitatively we have something like this. And again, this is our M2. We have an M2 profile. Okay. And once we reach this point, we now know roughly what we expect our solution to look like. Now, whether I've drawn the curvature here exactly right or not, it's okay when we get to HEC-RAS if it doesn't look exactly like this, but follows the same trend of an M2 profile, we'll be fairly happy. Okay. So again, at this stage, we've basically just done what we've seen many times in class with our qualitative profiles. We've just drawn it for this particular problem. And now we're set up to go into HEC-RAS and actually put in some numbers, compute the water surface profile so that we can say at each depth, some point here, what is y? Okay, y equals something. We will actually be able to solve for that. Or say here, y equals something. HEC-RAS will allow us to figure out the water surface elevations as we move along the channel. Okay, so again, just to quickly summarize the preliminary steps before you start your model, you should fully define the geometry. Where does the elevation equal to 0? And so what's the elevation at your downstream and upstream ends of your channel? River stations. So what is the upstream river station? What is the downstream river station value? And again, I recommend the downstream set to 0 and then work your way upstream. And again, those are positive numbers, even though you're moving against the flow direction. And then you're fully described your cross-section geometry and set that up in Microsoft Excel so that you can copy and paste into HEC-RAS. Once you get that far, move on to your qualitative solution, as we've been doing in class, and just sketch a qualitative profile, which is exactly what you see on the screen right now, so that we have an expectation of an answer when we move to our numerical model, which we will cover in the next series of tutorials. Okay, that's it.